All right, good evening. It's about time to start. In fact, it is 7 o'clock right now, so I'm gonna get started even though there's only one person on the Discord voice channel. But I'm guessing some people are on the other side, on the YouTube side. Maybe, maybe not. So anyway, we're gonna get started today with the debugging of a program. So one of you graciously contributed a program for me to illustrate how to debug programs. So that is good because it's really kind of important to understand how to debug a program, and in that process, we get actually a deeper understanding of the material. So let's go ahead and get started with that. So this is the program. It is implementing the swap subroutine, and it is not working. So when you so obviously you're gonna only debug your own program, right? So you're not gonna. Oh, okay. I guess I muted. Right there we go. I was muted on the Discord side, and so you guys probably see me talking but cannot hear a single thing. So here we go. So we should be good now. So the program that I am debugging today is contributed by one of you, which is great. Okay, so and I can see there's a lot of effort put into writing the code as it is, but somehow it is still not working yet. So this is the first time I'm seeing it too. So this lecture is definitely not one of those prepared sessions. I mean, in general, I don't really prepare my lectures the way that other professors do it. Alright, so main is provided, so I'm not gonna have any suspicion of main, and we'll start with swap itself. So we can see the stack picture in here is correct. Okay, so PTR2 is the last argument. It is pushed first, and then PTR1, and then we have the return address, and the return address in this case has a label of main underscore return from swap. And in the more recent notes, we do not use a label anymore because this program, or the main, is coming from a version of the assembler where that's before I implemented the dot notation. So that's why it's a little bit different. And here we have t, which is 1 byte below the return address, and that is correct as well because t is a local variable, and local variables can only be allocated by the subroutine itself. So that's why it is allocated last and has the lowest location on the stack. So we got this much of the stack is correct. So now we check the labels. T has an offset of 0. That is correct because the stack pointer should be pointing to T after we make the adjustments. And then local var size is t1 plus. That is correct as well. T is the last local variable, and 1 is the size of t. So t plus 1 is going to be the number of bytes that we need just for local variables. Main return from swap. Now that can potentially be a problem because now we have two label definitions that are defining the same label, because we see that there's one label here and there's one label here. So I'm suspecting the assembler would actually complain about this because we have two different definitions of the same label. So we'll kind of flag it. Okay. So I'm gonna. Oh, okay, wrong line to have the comment, but I'm gonna flag it here and say the assembler should. Okay, typo. Complain about this. Okay, so so other than that, we want to know. So in here, okay, so the two labels are serving different purposes. This label here is telling us where do we go back to main to continue execution. This label here is for the most part useless. Usually I just say it is a return address, RET ADDR. which is, oh, I probably should not be deleting the text so that I can test whether the assembler is going to catch it or not. But what it really is supposed to be is the offset from where the stack pointer points to the return address on the stack. So the meaning of this label is entirely different from the meaning of that label. Are there any questions about what I just talked about? All right. So if there are no questions, we move on. So assuming this is return address, RETADDR, which is the offset and not the actual place where we need to return to, it is the correct label. Are we looking over someone's code? Yes, I am looking over someone's code. Someone could not get this program to work, and so I'm using this as an opportunity to illustrate how to debug a program. So we got PTR1 is the return address 1 plus. So once again, this label definition, probably should be flagged. But other than that, PTR1 is defined correctly, and then PTR2 is 1 byte after that, and that is defined correctly as well. Alright, so given that I have this really strong suspicion that the assembler should catch this, and this is at least part of what the problem is, so that's one of the techniques of debugging when we have basically really kind of good tools for debugging. Because in the past, if you're writing a program for a mainframe computer, you can only run that program overnight, okay? And then the next day you collect the output, but you won't be submitting the job again until the end of the day. So you cannot really use iterative debugging back in those days. But in this case, well, as long as you're familiar with the tools, you can really kind of make some changes, put it through the assembler, run the program again, and so on. So I would strongly recommend to fix only one or a few problems at a time, because a lot of times, the other problems would either resolve on their own, or they will give you a different symptom, once you fix an earlier bug. So my recommendation is not to fix everything and then run it through. Just fix a few things, but you want to do it in the order of how the program is going to execute. So we'll go ahead and get out of the editor, and then we cat this to xclip, cell clip. Obviously this is only needed because I was using a command line editor. And now we get to the assembler, and I really don't need to use this secret assembler, but yep, there we go. Because this homework assignment was due on last Thursday, if I remember correctly. And there's a homework assignment due this Thursday. That would be the last homework assignment. Alright, so we get to here, we paste, and then we want to see if the assembler is going to complain. Alright, so we go to swap subroutine, and it did not complain. Okay. Oh, it did. Okay, there we go. So it did complain about the label main underscore return from swap was defined on line 30. And if you go back to line 30, that's actually correct. It actually took me quite a bit of work to detect a label being redefined, and also to have to point out where it was defined first. So, well, it comes in handy, right? Okay, so we want to fix this first, because without fixing this, the program does not even assemble, and if the program does not assemble, there's no way to run it. So now we get to the subroutine, and then we change this label. So main underscore return from swap is a label to designate where we are returning to. Return address, on the other hand, is an offset. It is an offset from where the stack pointer points to where the return address is supposed to be stored on the stack. Okay, so if this is a little bit confusing, that's okay. What I'll do is I am going to draw a picture. Okay, so we'll switch to picture mode, which is right here. Alright, so there are two labels. Okay, they're both labels. One is a label designating a place in RAM. So if I look at this entire thing as RAM, okay, this is where the program is. Okay, the program starts from location 0, 0, and it goes up. Okay, this is where the program is. The stack, on the other hand, starts with location FF, and it grows downward like this. Okay, now obviously if you have a really big program, you won't have as much stack space, and if you do run out of stack space, it will just kind of run into the program space without any warning, because this particular processor has no such thing as a protected mode, so it doesn't detect that you are stepping on something that you're not supposed to. Alright, so the first label, which is main underscore, okay, I'm just looking for the name of that thing. Well, I just changed it, so let me go back to main here. So it's main underscore return from swap. Okay, and I'm switching back to the browser so you can see where the label is. So that label really is bookmarking or labeling a location of the program, because that is designating where the subroutine is supposed to go back to. On the other hand, we have return address. So return address is basically saying, well, when we call swap, it is going to use up some portions of the stack. Now exactly where on the stack, it depends on where we are calling swap from, and the caller, how many local variables the caller has, and so on and so forth. So we really don't know where on the stack is the frame that belongs to swap when swap is called. So we just know that it's somewhere on the stack. Okay, so we will just go like, okay, this is the frame of invoking or calling swap. Okay, so when we refer to the name of a frame, it includes several things. It includes all the arguments that is passed from the caller. It includes all the local variables, but it also includes the return address. So, and we also know one thing. Okay, when the frame is fully constructed, we know the stack pointer is going to point to the last byte that we allocate on the stack in the frame. So this is what we know is, okay, everything is relative to where the stack pointer points to. So now we take a magnified picture of that portion, which is really just a frame. So we know that D is pointing here. So the first thing, or the very last thing I should say, the very last thing that we allocated was the local variable T. So D is pointing to T, and one byte on top of that is the return address. So this label return address is the offset. It's answering the question of, okay, I know where the stack pointer points to, but once I know where the stack pointer points to, how do I find the return address? It is an offset to a location. The content of this location is going to be the label itself. So the content of this location is indeed main underscore return from swap. Okay, so that means if you want to use a pointer, this location actually points back to here. Okay, well, I didn't quite land at the right place, but you get the idea. Okay, so this byte here is actually an address, and it is the address corresponding to the label main underscore main return from swap. Okay, now but this is not the entire frame yet. Okay, because we have the two pointers, the parameters from the perspective of the called subroutine. So we got PTR1 and PTR2. So we can see how PTR1 is 2 bytes after the location that register D is pointing to, and then PTR2 has an address that is 1 past the address of PTR1. So that means T is basically 0 because it's an offset of 0. Return address is an offset of 1. PTR1 is an offset of 2, and then PTR2 is an offset of 3. So are there any questions about this explanation. Okay. If there are no questions, we will switch back to the editor, and that will fix the error, the assemble time error. So now the question is, well, do we know whether this code works or not? Now here you kind of have a choice. So you can either be super optimistic and say, we'll just run the code and see what happens. Okay, we'll throw it at the wall and see if it sticks, right? That's one way to do it, which is not wrong. And the other way is to analytically go through the code and figure out, every single line and make sure that those lines are correct. Now, which way are we supposed to use? Well, I can't tell you. Okay, that's a kind of personal thing. It's kind of subjective. Some people use a mixture of the two. Some people prefer to just run the code and see where it stops working. And some people like to analyze the code and entirely before they run it to test it. Okay. And in the test, you will be given questions like this. Okay, I'll give you a program. I'll give you the source code in C. I'll give you the faulty code in assembly, and then your job is to fix it, right? So, and because this is a remote operation, and I will let you guys use the assembler. You can use LogicSim. You can run the program. You can use the trace analyzer. In other words, as long as you're not collaborating with somebody else, all the tools that we use in class, in the lab, they're all available to you. So now the question that you need to ask yourself is, what works best for you? Okay, do you like to analyze the code, annotate it, and try to figure out where the problems are, or do you want to run it? Now, running the code means you still need to know what the code is supposed to do. So you still need to know, okay, I think this code is supposed to blah 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 blah, and then look for that. Okay, if that is missing, then you know the program is not working. But then the problem is, when does it start to deviate from the path that you think it is supposed to take? That becomes the question. So we're going to use that approach. Okay, we're going to run the code without fully analyzing it and see if it works. Okay, so we'll save it. And I'm not going to repaste the modified code, because it is simple enough of a change that I can just go ahead and change the cells that are incorrect. Okay, so we'll change this one first. And this one is supposed to be just return address, like that. And the next line also needs to change. And this is where it can get a little bit tricky, because if you fix the first one, which is the definition of the label, the error goes away. The syntax, or not syntax, but the assemble time error goes away. But the program is not fixed, so you have to change this one to return address 1+. So now the code is should be all fixed as far as the offsets are concerned. So we go to RAM file, make sure that we see version 2.0 raw. Download the CSV into swap.csv, and I haven't rebooted the computer from last Thursday, so we are replacing the file that I created last Thursday. This is one of the cool thing of running Linux. I really seldom have to reboot the computer. In fact, if I use the command line called uptime, I can tell what was the last time I rebooted the computer. Well, it's been 9 days. So, which is not really that much. I mean, on servers, I have had like more than a year without having to reboot the computer. So that's kind of nice. All right. So now we're gonna run the code on the command line. Okay. So we'll go ahead and okay. This is perfect. This is exactly what we want, because I named the file exactly the same way. Oh, I'm using Debian Linux. I'm using SID, which is the unstable version, and it is surprisingly stable. Okay, even the unstable version of Debian is surprisingly stable. I mean, occasionally I do run into issues, once in a long while, but it's not really that bad. Alright, so now we got the TSV file, and it's time to go to the trace analyzer. So this is the non-secret trace analyzer. You guys can follow me along. I mean, you can just kind of follow along and go to the same Google Sheet. Oh, okay, well, someone is already here. Good job. Alright. So now we import. Okay. So the key is, how do I know whether the program works or not? Okay, even just because I have a trace and a trace analyzer doesn't mean that it's really easy to spot whether the program works or not, and if it does not work, what is wrong with the program. Okay, that's actually not easy to figure out. And I have a little exercise for you guys to use if you want to. That can really kind of help you get familiarized with the symptoms of how a program can go wrong. Okay, but before that, we're going to go to Summary tab. We know there are 262 rows, so we just skip all the way to the end. All right. So once we skip to the end, we can see that the program did stop at the correct halt instruction. That's good. Okay. We also know that the stack pointer is balanced. That is very good as well. Okay. So now we go back and see if the content at the two locations were swapped correctly. So to understand which two locations we are talking about, we can see how 03 is stored to location FE and 07 is stored to location FF. So if we look at this from the pictures perspective, the main has its own frame, except it doesn't really look like a real frame because it's not called, and as a result there's no return address. But main is actually having its own frame. So this is the main frame, which is not referring to those kind of I was about to say really old and ancient computers, but that would not be an accurate description because mainframes survived and they keep evolving. They're very powerful today. It's just that they're super backward compatible, so programs written in the 50s in COBOL can still run without any problems on a mainframe that was manufactured yesterday, with gigaflops of processing power. It would just run those programs like super fast, but it can run the same programs written in from the 50s. And if you think about it, okay, many of those developers have passed away already, and yet the programs that they had written in the 50s can still continue to run on a modern architecture. So there's a lot of work going into maintaining that kind of backward compatibility. So it's kind of interesting from that perspective. But getting back to our topic here. So when you look at the frame of main, okay, so the frame of main is kind of deformed because it doesn't have a return address because nobody called it, okay? It just starts execution on its own. And it also doesn't have arguments. That kind of makes sense, right? Because if nobody is calling main, then where would those parameters be coming from? Nowhere. Okay, so we start with the local variables. It only has 2 bytes being used for local variables. Now with these 2 bytes, which one is which one? Which one is X and which one is Y? Well, it's kind of up to you to decide. Okay, there's no specific ordering that you need to follow. Because this is not an agreement between the caller and the callee. This is all within the callee, okay? So as long as the callee is self-consistent with which one is X and which one is Y, everything is good, okay? Because it's not communicating, it's not using these 2 bytes to communicate with somebody else. There's no caller-callee agreement here. So I think in my program, okay, let's see. This is location. Okay, I shouldn't say that. Register D initially is pointing to the last byte allocated, And this is the one that has the 03, and this is the one that has a 07 in it. So the program is supposed to swap these two bytes, okay? And we see that the program did not do that, right? Because when we look at the trace analyzer, we do not see that location FF has changed. We do not see the location FE has changed. Now, how can we check that really fast? The way you do it is you can look into a particular column, and I think it's Control G that can start the search. It's finding in the sheet. Okay, maybe not that. Let's try Control F. Same thing. All right, and let's cancel that. And instead, I would go to Edit and use Find and Replace. There we go. Because I want to use, I want to be able to specify more than just, oh, this is what I'm looking for. Okay. You can use regular expression, which is very handy. So that's what I'm going to use, is to search using regular expression. And well, once you select that, it becomes case sensitive. So we're looking for the asterisk, but when you look for asterisk as in a regular expression, you have to backspace it first. Backslash it first, because that's an escape. Otherwise, asterisk means any number of whatever is before that. And then we look for FF equals to, and we're only looking for one single equal to. So the next one should not be equal to, and instead it should be a hexadecimal digit. So we can specify that by saying it is 0 to 9 and an A to F. Okay, so it has to match one of the characters from 0 to 9, or A to F. And we also want to search this not and we only want to search within this particular sheet, and then we just click Find. So here is FF gets 7, and that's where we started, I think. Yep. And then let's find again. Oh, okay, so it did swap. So I stand corrected. It did switch. At least, FF got changed. So now we want to see if FE got changed too. So that's FF, and FE is changed as well. So the program got the job done. Okay, it actually did exchange the content of the two locations pointed to by the arguments passed to the swap subroutine. So it did work. So other than that label definition, the program was not, there were no further bugs in the program. All right. So are there any questions about this particular debug session? No questions. Okay. So if there are no questions about this particular debug session, I can give you guys some exercise that you can do. Okay, and whether you want to do it or not is entirely up to you. So remember how I gave you the swap solution, the solution to the swap subroutine. I gave you that on last Thursday. And on this Thursday, I will give you the solution to the Fibonacci function as well. So we know those programs work, right? So what we'll do is you can intentionally mess up a program that is known to work. Now, that is a very controlled experiment because you can make one change at a time. So you can say, I'm not really quite getting why we have two LDAA, okay, in the program. You go like, okay, so I can spend the time to try to understand it, but I can also just comment out one and run the program and see how it would deviate from the path that it's supposed to take. So that is a very interesting way of learning because you are intentionally injecting a bug in a otherwise correct program. So if the program doesn't work and it does something strange or wrong, it has to the origin of all those symptoms has to come from the change that you just made intentionally. So that is one way of learning the material of this class. Now this way of learning is tricky in a way because there are so many places where you can say, I'm going to change this line to blah blah, and we'll see what happens. Okay, how is it going to change the rest of the program? So before you make that change, you really should have um, a mental picture of how the program is supposed to work differently and incorrectly, with that change. So the observation using the trace analyzer is really just to confirm your suspicion, but it is a powerful way of learning the content of this class. So are there any questions up to this point? Okay, I'm drinking my coffee, so in other words, I'm giving you guys a little bit of time to think of any questions at this point. This is the last lecture because on Thursday we have a review for the final exam. Obviously my mic is very good. It picks up all the slurping sound. Alright, so there are no questions. Very interesting. Okay, that's okay. Without any questions, I'm going to show you something that I may or may not have shown you because sometimes my mind is kind of jumbled up from previous classes because I remember I talked about this, but was it this semester or the previous semester? Kind of like getting stuck in a time loop and you cannot remember did I do this in this iteration of the time loop or the previous iteration of the time loop? Anyway, so I'm going to show you this anyway. So if I have shown you already, just let me know. Okay, so I'm showing you I think that should get me. Nope. Okay, doesn't quite get me to where I want it to go. There we go. So I'm gonna go to the UC Davis, this link here, and okay, that's not where I want to go. I think it's under develops. There we go. Develops. Okay. All right, that's correct. So there is a real-time kernel. Have I talked about this before? Does anyone want to chime in if I had? Okay. So this is a real-time kernel that I wrote, a long time ago. Okay, thank you, Daniel, for confirming. So this is a real-time kernel that I have written in a long time ago for the AVR. MCU is not Marvel Comic Universe. MCU stands for Microcontroller Units. Okay, and that term way precedes Marvel. Well, Marvel Comic Universe. Okay, because the comic books comes a long time before microcontroller units. But anyway, cinematic. Okay, thank you. Marvel Cinematic Universe. All right, so that is correct. So anyway, an MCU is kind of a miniaturized computer, and I did say computer, not processor, because it contains RAM, it contains the ROM, where the program goes, and it uses the Harvard architecture. And I'm pretty sure we talked about the Harvard architecture just a little bit, because I think Aiden brought it up and asked what is the difference between the von Neumann architecture and a Harvard architecture. So for this discussion, it's not important to understand what is a Harvard architecture. All we need to know is we have a single chip computer basically that costs about, well, it depends on the version that you get. They can go from anywhere like 50 cents all the way to maybe about $15 to $20. Okay, it depends on how many you order at a time and how much RAM and flash space you want to have on it. Okay, but they're very inexpensive, and they're 8-bit processors inside, and these are used in Arduino boards. So if you look up Arduino, which we have done before, those are very inexpensive and relatively small circuit boards. I believe 1 year, I think it's the Science or the Astronomy Club of ARC, they launched a balloon with an Arduino board on it to collect data from upper atmosphere. So that was kind of cool. Okay, they made the entire thing and they collected data using a balloon that goes all the way up to I think 30,000 feet or so. Anyway, um, but the MCU is really just the MCU. Okay, it doesn't have an operating system. You kind of write programs the way you do in this class. You start from scratch. But that also means you cannot use multi-threading. So when you have a few things that you need to do, like, okay, I need to monitor this sensor, but at the same time, I need to control that, and I need to monitor that sensor. So if the logic requires, multiple threads naturally, and your program cannot use multi-threading, then you have to use, some really obscure way to emulate the effect of multi-threading. Can it be done? Yes. Okay, there are interesting programs in the world that makes use of a single thread to handle multiple things at the same time. And I know I'm digressing even further, but if anyone is interested in what program, what is one of the most representative program that is single threaded, but it can handle multiple things at the same time, it is Squid. Okay, so Squid is a proxy server program. So if you look into squidcache.org, that's the Squid that I'm talking about. Okay, so it's basically a caching proxy server, which means let's just say that you're in charge of the IT of the Los Rios district. Okay, and we know that a lot of people are interested in certain things. So the what Squid does is it will get it, but then it will cache it locally in Los Rios. So the next person going to the same web address doesn't have to go all the way out to get the content because it is stored locally in the cache. So this way it can optimize the traffic going outside of the Los Rios network instead of having like a bazillion network connections going out to get the same thing. It will get it once, look at the expiration time, and just say that, hey, before the expiration time, I'm just going to serve, I'm going to serve the request from inside the Los Rios network using the cached item. Okay, so you can kind of imagine this thing has to handle many connections at the same time. Okay, and all those connections are going at different speeds. Okay, some computers are really slow, some computers are really fast, some network connections are really slow, some network connections are really fast. So to do all of this stuff here using a single thread, the code is very interesting to read. Okay, I'm just gonna stop here because I can go on and on and on about this. So I'm gonna stop here. So the idea is to implement a real-time kernel so you can actually have multi-threading. So when you use multi-threading, okay, you don't want to write an entire program in assembly because that's a chore. Can it be done? Yes. But do you want to do it? Probably not, because that's the whole reason why we have the C programming language. Was the inventors of Unix from Bell Labs, was originally writing the entire operating system in assembly, and very soon they discovered, no, this is not what we want to do. So C really was intended as a higher level language that is very easy and very friendly to be compiled into assembly code. It's intended as a low level language, not as a very high level language. Okay. So anyway, I just want to show you some stuff here. Now these are the actual source code. So if I click on this, okay, it doesn't really show the source code, but it just trust me. Okay, this is the source code of the real-time kernel itself. It's all written in assembly. Okay, but when we look at the API, okay, so the API has function calls that looks like this. Okay, this is not in assembly. This is actually the prototype of a function in C. Okay, it's a void function. The first parameter is a pointer to a struct thread, right? And then if you go to one of the header files, you can actually find out, how thread or struct thread is defined. Okay, right here, struct thread is, I talk about what it is, but I don't give you the actual definition. But you can see that, hey, okay, so So the API is intended for C. So you're writing a C program, multi-threaded, and you make use of the real-time kernel to do certain things. So we can see what things we can do here. You can kill a separate thread. You can kill the thread that you are running on. You can add a new thread. In other words, you're adding more parallelism to the real-time kernel. And if the thread that you're on, has nothing to do right now, you can yield so that other threads can execute. You can schedule a thread to execute within, a certain number of ticks away from the present time. So you're basically saying, okay, I know I don't need to read that sensor for the next 20 milliseconds. Wake me up in 20 milliseconds. That's what the schedule is for. And then we have semaphore P, semaphore V, and so on there for synchronization between the threads and so on. Okay, but these are all written. These are all intended for C. So now you got an interesting problem because we want the API to be usable by C code, but the actual real-time kernel is written in assembly. Okay. So does that ring a bell about what we were talking about on last Thursday? Because on last Thursday, what we talked about was the agreement. Okay, so this is all about agreements. It is about the agreement of subroutines of how they understand a structure. Okay, we are not going to have a whole lot of time to really kind of get into this. But I do want to show you why that content or why that material is useful. So, so talking about this is interesting, well, at least to me, but it may not actually give you a sense of what it looks like. So I'm going to show you the actual code, the actual real-time kernel code, and also the application programs that makes use of the real-time kernel. This is used in a lot of projects. It's used in one of my consulting projects. So we'll go here, and T10B is the name of the circuit board. Okay, and it's under firmware. Alright, so here we got rtk.s. So this extension, uppercase S, is a standardized extension in Linux that signifies that the file is written in assembly, and because it's an uppercase S and not a lowercase s, that means it's supposed to go through the preprocessor as well. So macros would actually work in this file. And you can even see that the comment is very much the same as in C. Okay, but the rest of this program is written all in assembly. And you can see that this architecture is really kind of friendly because it has got push instructions. So instead of doing what we have to do, which is decrementing the stack pointer and then use st to store a register to where the stack pointer is currently pointing to, it actually has a nice instruction to do push. And there's another instruction to do pop, there's another instruction to do call, and another instruction to do return. So the architecture that we are using, text toy processor, is actually more RISC compared to the AVR architecture. But if you just kind of scan through this code, it is all in assembly. Okay, there's nothing here that is written in C. However, when you look at rtk.h, okay, it's a header file intended for C and C++. Now you get to see, oh, okay, so we have the structures actually defined in C. Okay, so now the way this works is I have to mentally keep track of how structures are compiled and understood in C code, and then I make the corresponding labels to make my assembly code be able to access and manipulate structures. Okay, so I use tick here. Okay, so if I go back to rtk dot, I think there's a include file for all of this stuff here. Nope. Okay, guess not. So we look here and see if tick is defined. What I'm looking for is the label definitions that we use. I can find one here, thread underscore next, because thread is the name of a structure. So thread underscore next is the offset from the beginning of a struct thread to the member that is called next. And I can probably look for the definition of thread underscore next from the assembly files. There we go. Okay, so the way I define a label, called threadnext, this is how it is defined in this particular programming language or assembly programming language. So instead of saying threadnext colon thread underscore sp2 plus, we use there's a not mnemonic, but there's a directive called .edu that allows me to define a label. But in my assembly language for the toy processor, I decided not to use this syntax to define a label. But the point is, these labels defined in assembly is how I can access members of a structure. And much like what we talked about on last Thursday. All right. So are there any questions at this point? I mean, this type of programming, by the way, is called well, it is a subfield of embedded system programming, but this is low-level embedded system programming because I'm implementing a real-time kernel, so that application programs can make use of multi-threading. So are there any questions? Is anyone interested in this kind of programming instead of the usual, app development that most people do? Not a whole lot of people. Well, let me ask you, how big do you think this real-time kernel is? In other words, how many bytes do you think the real-time kernel is? What is the footprint of the real-time kernel? You can have your own guess. You don't even have to type it. Okay, at least 12. Okay, so the real-time kernel itself is 2 kilobytes, 2,000 bytes. Okay, it is not small. Okay, I didn't actually spend a whole lot of time to optimize the code, but it is 2 kilobytes. The Arduino board makes use of a processor that has 8 kilobytes of built-in flash memory. Oh, okay. So getting back to the footprint first, okay, and then I'll address what is written in the text channel. So so that means I have, out of 8 kilobytes, the real-time kernel takes up 2 of the 8. I still have 6 kilobytes for application code. Now you might think 8 kilobytes is not a whole lot of space. Well, it really is kind of a lot of space. It depends on what kind of program you're writing. I used to teach a robotics class at UC Davis where students have to write code on a robot that can explore a maze, remember the maze configuration as it explores it, and then find the shortest path and control the motors to get to a certain location. Those programs do not exceed 32 kilobytes. So yeah, so we are talking about having a modified version of Dijkstra's algorithm written in C, and even with that and all the motion control stuff, it does not exceed 32 kilobytes. So we can kind of understand that this kind of programming is a niche kind of programming, but there's an increasing demand of this type of niche programming. Just think about Roomba, the vacuum cleaner that can kind of move around and know where to go back to recharge itself. That's one application. Okay, and then there are probably going to be a lot more applications, considering how drones are getting taking off literally. Okay, there can be a lot of stuff that can be automated. And anytime you want to automate something, there's high level code, there's low level code. Low level code usually refer to interfacing with the GPS or interfacing with the camera or the motor control, stuff like that. And then there's high level code, which has to do with path planning, path correction and other things. So there's a whole lot of complexity when it comes to automated whatever. Okay, it can be underwater, vehicle, can be drones, can be cars, can be just about anything. But every time you want to automate any type of robotics, there's a lot of custom code, and multi-threading is going to be important in all of those programs. So I'm going to go back to the text channel, and somebody wrote, it's interesting, but it's hard to understand. Let me give you this idea. Okay, so I know this is a digression, but since I really don't have enough time to give you something that's meaningful, because I can write a program, but it's not going to sink in. So instead, I'm showing you why this stuff is important, and hopefully it helps to open new doors for some of you, because now that you understand that, so there's an entire branch of programming that is not really just using Google Script or using Unity and other types of quote-unquote standardized programming environments. So this time I'll go to digikey, which is an online merchant for parts. So we'll look for AVR, okay, which is the name of the architecture that we just talked about. And there are 4,000 something matches, so we're going to narrow down by looking at just microcontrollers. And once we click that, you can see that it becomes a much more parameterized type of search. And we can look up by manufacturer. We can also look up by series, which is not what I would do. So what I'm going to do is kind of scroll all the way, not entirely, but I'm going to scroll here to RAM size. Okay, so you can see the smallest one only has 32 by 8-bit, in other words 32 bytes of RAM. And that's not actual RAM either, because it has 32 registers. So registers can be seen on this architecture as RAM, but it can also seen as quote-unquote registers. Okay, so it's kind of interesting because a portion of the RAM space is are the registers. So let's pick one that is somewhat interesting. So we'll pick 128 bytes. Okay, so these are all counting the 8 here, the x8, that 8 is referring to bits. So we apply that, and we see that there are quite a few options left. So we'll take oscillator is internal. So by doing this, I'm looking at parts that are very, very self-contained. They don't need a lot of extra parts. They can be utilized, really, really easily. We'll also look at the packaging, and we'll just say that we want it to be an 8-pin SOIC, small outline integrated circuit. So we have very few options left. Voltage, operating voltage. We'll get to the low voltage range. Okay, so this way it can be powered up by basically 2 AA batteries. So we apply that, and that narrows down to just one single part. Then you go like, but what does this have anything to do with assembly language programming? Why do I want to know this? Well, there are a few things that we want to kind of check out. The first one is how much is one part. Okay, and they changed the website, so it's not as easy to find pricing information. Oh, okay. Quote required. Okay, so they won't let me know exactly how much it is. That is not nice. Okay, so we can just look at some of the other parts. So we can see that if you buy, I'm just looking at how much, what is the minimum that you have to purchase in this case. So if you just buy one at a time, this particular part is going to cost you $1. Okay. On the other hand, if you buy in volume, okay, if you buy in quantities of 250, for this particular part, it is $1. And so they're very inexpensive. Okay, that's the bottom line, is they're very, very inexpensive. But remember, we also specified that we only want to have 128 bytes of RAM. So do you think you can compile a C program to make it work using this architecture? With only 128 bytes of RAM, that's your entire stack. Well, the answer is no. Okay, you cannot write C programs on something with this little resources. But you still want it. Okay, let's just say that you want to make the next Furby. Okay, you want to make Furbies the next generation. Well, you can put in a kind of really powerful processor in a Furby, so it can do all kinds of stuff. I mean, well, actually these days, I would not be surprised if Amazon releases a Furby that has what is the name of the Amazon voice assistant? Alexa. So I would not be surprised if Alexa can be integrated into a Furby, so that children can talk to their Furbies and ask, Furby, I would like you to place an order of blah 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 for me. Yeah, that's gonna happen whether we like it or not. So the bottom line is, this kind of processor they're very inexpensive. They can do a lot. Okay, even though there are only 8 pins on this particular integrated circuit, it can do digital control. It can sense voltages. It can even output quote unquote analog signal. In other words, it can output quote unquote a range of voltages. Now it's not exactly quite that, but it's close enough. Okay. So you can use it to control a lot of things, and it only costs you $1 each, okay? Which means you can put it into very, very inexpensive products and automate certain things. We are talking about potentially screwdrivers, okay? So that the screwdriver can sense torque, okay, and use Bluetooth to transmit out, the data. So your app running on a phone can tell you, okay, don't strip that screw over there. You have enough torque applied already. Don't apply any further torque. Okay, so we are talking about applications like that. So now you have to ask yourselves, how many potential applications are there out there? We are talking about putting single $1 processors into whatever you want. Okay, the power requirement is very, very small. At least 12. I would say at least 42, right? I mean, 42 is a better answer than 12. No, I'm just kidding. But there are tons. Okay, many years ago, I told my class and go like, you can use this to make a smart backpack. Okay, not only can the backpack display different patterns of LEDs, but it can even have motion detection, so it can warn you that somebody is approaching you from the 6 o'clock at a certain speed that is suspicious. Maybe you can even auto fire pepper spray backwards, okay, to the person who's approaching you at a high speed. It can all be done. I mean, I know these ideas sound really ludicrous, but guess what? It can be done. And the backpack is not even going to cost a whole lot more than a usual backpack, because the controller is only $1. And it doesn't need a whole lot of support circuit to get it to work either. And then we got some text here. Imagine running to your friend and surprise them. Maybe we can have a friend or foe identification system. That might be helpful, right? So your friends will all have a little dongle, that identifies as friends. And if a person approaching you has a friend identification, then the system would not trigger. That's entirely possible. So I'm throwing out these kind of crazy ideas just because, from the financial perspective, it is now doable because of these very, very inexpensive parts. But they are so the resources is so little that you cannot write C programs. So what do? You write programs in assembly. Okay? And the upfront cost of software development, yes, it's going to cost more because it would take more time to write the same kind of program in assembly. But the offset has to do with the manufacturing cost of the device itself. Okay, so if you're planning to sell, let's say 50,000 of these backpacks, okay, then lowering the manufacturing cost per backpack is very, very important when it comes to maximizing profit. Now, 50,000 is nothing. Okay, when we are looking at an international kind of market, 50,000 is like that. Okay, it really is nothing. So this is the kind of market that we are looking at. If anyone goes to Alibaba or AliExpress, okay, they basically sell direct from China to international market. There are a lot of quote unquote smart devices, okay, bicycle pumps, okay, for 20, I cannot remember, I think it's like 20 or 30 bucks, you can get a rechargeable pump that has a programmable pressure gauge, and it will just charge, or it will pump up to the set point, and then it will stop automatically, and it's USB charged, and that's like $30, okay, and it has a certain level of quote unquote intelligence in it. So that means we are looking at a potentially is an explosion of applications that can make use of these tiny little controllers. Even if you're thinking about, but what about Tesla? Okay, the car. Okay, obviously these tiny little processors would be useless in the Tesla. Well, that is actually not the case. Okay, because Tesla is a very complicated kind of application, and I'm looking at the text channel here. It's also a very good website to check if a product you're looking at is a scam. Well, so far I have not been scammed. Okay, so knock on wood. Anyway, Tesla. Okay, that's right. So we are talking about Tesla. So even though Tesla is a very complicated application, and certain parts of Tesla would have very powerful processors running Linux or some advanced operating systems. But there are other devices in Tesla where they say we don't want anything too complex. Okay, we just want something that is simple. Get this little job done, and get it done reliably, and be able to be controlled by the main controller using a network, and that's all we need. Okay, so we still have applications of tiny little processors like this. Okay, for I guess dome light control. Okay, so the dome light itself is quote unquote intelligent. Okay, it can be controlled by the main there's a name for that, but then by the main processor. But at the same time, it is intelligent on its own, so the main computer is really just sending configuration data and not directly controlling the dome light. So the dome light can operate on its own. So when it loses communication with the rest of the network, it'll just light up. Okay, because it will think that, okay, this is an emergency situation, I'm gonna light up if I can. And if you put a tiny little LiPo battery, inside the dome light itself, it can even be pulled off, from the vehicle and become its own tiny little flashlight on its own. And you can press a button, it will send out the SOS signal, and so on and so forth. Right? I mean, just think about the possibilities. Okay. So this is the background that I came from, which is embedded system programming. But when I was in that particular industry, the best we could do was a single board computer that would cost like $200 or $300 back in 1990. That's a lot of money. Okay, so now we only pay $1. Okay, for a tiny little chip that can run on 2 AA cells for a long, long time, and yet it has more processing power, and it has more capabilities when it comes to digital versus analog input and output and so on, compared to a $300 board from the past. So I hope this is illustrating a possible path for some of you to pursue, once you graduate from a 4-year university, because I think this is a very interesting field to get into. There's not as much competition because a lot of people do not know about these special types of programming, and a lot of people do not like assembly language programming to begin with. And I'm gonna guess half the class belong to that category, which is okay. I think it's pretty normal because assembly language programming is very, very unnatural when it is compared to your other programming classes. We got some text coming in. So if you guys have any questions about embedded system programming, these particular devices, I can talk about this, just kind of offline, using Discord. Oh, okay. I thought somebody was typing on the text channel, but I was not. It wasn't there. Okay, there's no new content. All right. So that's my spiel, of this kind of assembly language programming. So, are there any questions? What about the homework assignment that is due on Thursday? Are you guys done with it? Have you gotten started with it? No. Okay, so we got more text coming in through Discord. Just waiting for the message. All right. Yes. So the question is this type of programming used in BIOS in computers as well? The answer is yes. When a computer starts up, no matter how big of a processor you purchase, they all wake up in x86 mode. In other words, they all wake up thinking that, oh, I'm just a wimpy little 16-bit processor, until they find out that they're not. Okay, so the BIOS starts up, and the first thing it needs to do is to look for RAM. It's like, okay, where is RAM located? And BIOS has a lot of stuff to do. BIOS stands for Basic Input Output System, and that's the first program that your computer executes when it is powered up. Okay. Okay, and somebody said working on it. Okay, and I'm assuming that it is referring to the Fibonacci program. Alright, so let's talk about the Fibonacci program because I do have some recommendations. Okay, so if you guys have started on it, so let me switch back to the text command line interface. Go back here. And what I want to do is really just to look at the C version of the Fibonacci program. So uint8 underscore uint8 underscore t fib uint8 underscore t x or n. Doesn't matter. That's just name of the parameter. So I'm giving you one implementation of the code, which may or may not be exactly the same as the one in the assignment, but it will be close enough. Okay, and the point is, how do you write a program like this? How do you debug it? Okay. All right. So this is sort of maybe exactly the same, may not be exactly the same as the program that I put into your lab, but it'll be pretty close. Okay. So the question is, how do I write this code? Okay. So you don't want to write the entire thing, including the recursive call and whatnot, and then you run it to see if it works. Okay, that would not be a good idea. So the first thing you want to do is to simplify this so that you just want to check out things. Okay, am I getting the right things on the stack? So the first thing I would do is really just say fib and that. That would be the first version of fib. So you would go like, but that's pointless. I mean, this is stupid. Well, it's not entirely stupid because with this, you can actually run this code in the GUI version of Logisim, and be able to visualize what is on the stack. At least you can confirm that the parameter is pushed correctly on the stack, and the return address is also pushed correctly on the stack. So you know what the stack frame looks like at the entry point of the subroutine. Okay, so this is not exactly useless. Okay, if you want to know and visualize what is on the stack from the perspective of the subroutine, this would be the first version to do it. Okay. All right. So what do we do next? Well, let's go ahead and copy and paste this code, and I'm just gonna simplify the subroutine and say, let's just do that next. Okay. In other words, whatever argument you pass to fib is really the same as the value that's going to be returned. So you run the program using this and go like, okay, I want to see if this program works. Because if this doesn't work, then you are having problems accessing the parameter. Okay, so if this works, that means you know how to access the parameter n. Then you can move on to the rest. All right. So what do we do after this? Okay, if this program works, or if this subroutine works, what do we do then? Well, then you can compare. Okay, you can compare n to 2, and if n is less than 2, you return n. Otherwise, you just return some bogus number. Okay, I'm just picking 103 here. Because this way you can check whether your comparison is done correctly, and also whether you are branching correctly to get to the 103 when n is not less than 2. And then when n is indeed less than 2, then you just return n itself. So if you pass 0, 1 to n, as n to fib, it would just return the same back to you because it's just returning n. But if you're passing, let's say, 13 into fib as n, then it should return 103 as a constant. Okay, if this code works, that means you have the branching done correctly. Then you can start to do a little bit of recursion, not a whole lot. Okay, so if this works, then I'm going to introduce just one level of recursion, just that. Okay, not a whole lot. I mean, it really is just that. So when you do something like this, the program is going to return let's see, it's going to return 1 when n is greater than or equal to 2, because eventually, this n minus 1, will kind of reduce down to 1, and then it's going to return 1 because of the then branch of the ternary expression. So if that works, okay, congratulations. Okay, you got a lot of the components working already. You know how to get to n. You know how to compare n to 2. You know how to make a decision based on the result of the comparison. And you know how to do a recursive call. Okay? But just one. Okay? Now, if this works, then you can figure out the other one. To have a second recursive call. So every single time, if it works, you want to kind of make a copy of that program, in a folder somewhere, so that you can, if the program doesn't work anymore, you're adding some code, and then suddenly the program doesn't work, you can compare that version of the program, the one that doesn't work at all, with the previous program that works up to a certain extent, because then you can compare your code and find out, oh, I added these 5 lines, and then the program doesn't work anymore. What are exactly these 5 lines doing in the program? So this is a very gradual and, to a certain extent, systematic way of implementing the Fibonacci program. So are there any questions about working with the Fibonacci program? Okay, let me just kind of go back to that lab, the Fibonacci lab, because I want to make sure it is fun if you allow yourself enough time to do it. Okay, if you push too far, if you run out of time to do it, I think it may not be that fun anymore. So That's just me, nagging and saying, hey, don't wait all the way to the end to do this. All right. So I'm checking out this code to see if I'm giving you a main to begin with, because I don't want you guys to have to think about how to do the main. Okay, so it looks like I did not give you a main to work with. So I'm gonna do that right now in the next 5 minutes. Alright, so let me go here. I mean, if you have your main already implemented, just keep using yours, okay? There's no need to use mine. But if you want to use mine, that's fine too. I'm just going to use this file for the C code of main. So main is not going to do much, okay? All it's going to do, at least in C, is to declare a local variable, and it just says, local variable x is calling fib with a particular constant. Okay, so we can even use a symbol for this. Okay, we can say this is test value, and test value in C is using pound define, but in assembly code it's going to use it would use a label definition. So we'll define test value to be, try 0 and 1 first. Okay, so don't push your luck and go like, I'm going to try 5. No, test the cases where there's no recursion first. Okay. Alright, so let's just say this is main, and we'll split the screen, and we'll start to write. I'm gonna write the code in assembly. Oh, okay. My bad, not supposed to do that. Oh, no, that is bad. Forgot to save the file first. Okay, fine. And we want to use dash lowercase o to split. Oh, okay. Wrong direction, because I wanted to split left and right. There we go. Okay, so I'm gonna have to do it again because I just lost what I edited, what I just put in. Okay, so we'll make this hopefully really quick. Oh, I did provide main somewhere. Okay. So if main is already provided, then you want to implement the program really kind of step by step. The trace analyzer is going to be very helpful when you get to the recursive part, because without a trace analyzer, you probably won't know. Okay, it's really hard to see what is going on the stack, because this is not just a single. There are two recursion points, not just one single recursion point. Let me just illustrate what I mean by that. Okay, so the first recursion point, which is this one, it will leave behind something on the stack that you can see. But the problem is, when it returns, it will do a second recursive call, and the second recursive call is going to overwrite the stack space that was left behind by the first call. So that's why it can be very difficult to debug if you really just look at the RAM content using the GUI version of Logisim. That may not be very helpful because you're not seeing the whole picture. In order to see the whole picture, the trace analyzer is going to be extra helpful, because it really just every single instruction execution leaves behind a trace. So you can literally just read the trace analyzer output and understand exactly how the program executed. Is that going to be tedious? Absolutely. Okay, it is going to be tedious, and that's why you don't want to use a high value of n, because that just kind of go through a lot of calls and returns and calls and returns, because the number of calls and returns is exponential compared to the value relative to the value of n. So you want to try something simple first, like 0 and 1, and then try 2, which only has one single recursive call, because only one of them, well, I shouldn't say that. It does have two recursive calls, but it's a single level recursion. And then it comes back right away. Okay? So you want to kind of write this program incrementally and then test it also incrementally. That's my recommendation. Are there any other questions about this homework assignment. This is going to be your last homework assignment, but it's not going to be easy. So I do want to recommend getting started with this program early on. All right. So I don't have anything else to say unless there are questions that I can answer. All right. So I got one question from a person in this class about not really quite understanding the concepts. So one way to do it is to kind of watch the recorded lectures again and basically stop when there is something confusing. Okay, when there's something that you don't understand, you want to stop there. Now, when you don't understand something, when there's a confusion, it is usually because there's a concept that was not clearly understood to begin with. So you have to identify what that concept is, okay? And then you can ask me about that. You can also refer to even earlier lectures to see how that concept is explained, okay? All the sample programs that I have written in this class, you can use those, okay? You can use those in your final exam. You can use those to help you write the program, that is due on Thursday. So I do recommend that you kind of organize, okay, all the sample programs that I have written in this class. Organize, comment, annotate those programs because they are basically class notes for this class, okay, except they look like a program. So when you start to annotate those programs and try to explain what each instruction is doing, that's one way to study for this class, is really just to go through those programs and make sure that you understand what each instruction is doing, what each label definition is for. So once you have identified all of those things and be able to explain to yourself or somebody else, okay, studying together is not a bad idea. Answering final questions together is not a good idea, okay? But you can study together. So you can basically bounce ideas off of each other, try to explain a concept to the next person. And in that process, okay, I think a lot of people find it easier to understand concepts when they are trying to explain it to somebody else. Okay, so that's also a technique that you can use to study for the final exam. All right. So are there any further questions about the material of this class? All right. I'm not seeing anything, so I'm going to stop tonight's lecture. So I'll see all of you on Thursday, where we'll talk about the solution of the homework assignment of Fibonacci, and also to talk about the final exam. But I talked about that a little bit already. It's going to be you'll be presented with the C code, faulty assembly code, and then you have to identify where the program is wrong. But you can either statically analyze the program, or you can use Logisim, run the program, go through the trace analyzer and find out what is wrong with that trace. Okay, so we'll get to that on Thursday. And if you study a little bit, you can also bring other questions to Thursday's lecture. So it's basically really just a review of the material. And that's it for tonight. Okay. All right. So I hope you guys have a nice evening and get your dinner and then get started with the homework that's due on Thursday. And then I'll see you in 2 days. All right. Bye.